This lecture is a continuation of Chapter 9. We've talked so far about what we call simple gas laws, and that would be Boyle's Law, Charles' Law, etc. Now we're going to talk about kind of the foundation of this entire chapter, and that's the ideal gas law. And of course, I'll give it later, but just so that you're looking at it here. I do want to emphasize that all of these gas laws operate under an assumption that's not entirely true. I guess that's what makes it an assumption instead of fact. That an ideal gas has the following properties, in which some gases are clearly close enough to these properties that it's very safe to use these calculations and get a good approximation. Others are not, though. So this is part of the kinetic molecular theory, but just kind of to reiterate, the assumptions for an ideal gas are that the gas particles themselves are so small they essentially take up no volume in space, that there are no intermolecular attractions between gas molecules. Now, there are very minimal attractions, but in what we call real gases, there are some, and that starts the ideal gas laws, or all that gas laws start to fail when the gas particles have significant molecular attraction between them. So in a way, the ideal gas law combines the simple gas laws, except you can see there's a new variable introduced here, and that's the number of moles. So the proportionalities and relationship between the four variables are still the same. See, pressure and volume are still inversely related to each other. Pressure and temperature are directly related to each other. So, but what's different about the ideal gas law is we use it when we are given one set of conditions for a gas. So you may have a problem where you're given pressure, volume, and temperature and asked to solve for the number of moles, okay? Or it could be for any particular variable, whereas the simple gas laws and the combined gas law are when you have a gas, you know all of its properties at a certain set of conditions, and what you want to know with the combined gas law or the simple gas laws is if you change one of those variables, like if you change temperature, what is going to happen to the other variables. So simple gas law involved two different values for the variables, and the ideal gas law involves just one set of variables for a gas. So on the introductory slide, I talked about what an ideal gas is, but just kind of to help you remember, and it is something I'm going to expect you to know on your exam too, is under what conditions do gases act like ideal gases? When is it safe to use these equations? And those conditions happen to be under low pressure and high temperature. I'm going to explain the rationale for that, so you may have to listen a couple times to get it. So let's imagine we have gas particles like this, okay? And we are assuming that they do not feel each other. They do not feel the effect of each other. So we'll say no intermolecular forces. Okay, that's got to be true in an ideal gas to use the equations. But now let's say that we move away from ideal conditions for an ideal gas. Let's move away from low pressure. Okay, let's go to higher pressure. What's going to happen to these particles on a molecular level when you go to high pressure? They're going to be squished in closer together, right? So instead of the picture we have to the left, we're going to have this one at higher pressure. Now, why is high pressure not good for ideal behavior? Because you've squished the molecules closer together, they are going to start feeling the effects of each other, okay? So they will feel some intermolecular forces, and they're not going to behave so ideal anymore. And the answers you're going to get from the calculations under these conditions are not going to be reliable. The ideal gas law uses a proportionality constant called R, which is the universal gas constant. And it's just a proportionality constant, okay? It's what makes the product of pressure times volume be equal to the product of moles times temperature. So it's kind of our pivot point, proportionality constant. And it can have a bunch of different values depending on the units for pressure, volume, and temperature. So, for example, this is the one we'll most commonly use. If volume is given in liters, pressure is given in atmosphere, then the value for R you're going to use in all of your calculations is this one, 0.08206. But let's say that pressure is given in, volume is given in liters, pressure is given in torr, okay, then the R value you'll need is 62.36. So bottom line is, units are important here. Make absolutely sure that you use the R value that has units that match all of the other variables that you're calculating with. Here's a sample problem for you, and they're pretty simple. As with the simple gas laws, you mainly have to pay attention to units, that they all match. Otherwise, it's just kind of plug and chug. So pressure, volume, moles, and the R value that matches with liters atmosphere is 0.08206. And then we are solving for temperature. So we're going to plug in everything we know, rearrange to solve for temperature. And here's a little bit neater form. All right, so we're going to isolate temperature. And so we'll divide both sides by 1.62 and 0.08206. That's it. Plug and chug. Remember that the temperatures you're going to get out of any gas law is Kelvin. I have mentioned the conversion factor that we can use only for gases, that 1 mole of any gas occupies a volume of 22.4 liters. Now, it's important to understand that is true only under standard and temperature conditions, STP conditions. So standard temperature, just to remind you, is 0 degrees Celsius, which is 273 Kelvin. And standard pressure is 1 atmosphere, or if you're working in millimeters of mercury, 760 millimeters of mercury. So it's only true under those conditions, and I'm going to show you how that can actually be derived from the ideal gas law. So if you start with the ideal gas law and you rearrange it to solve for molar volume, and molar volume, just like molar anything, is how much of that variable per 1 mole. Okay, so like molar mass is how much mass is in 1 mole. Molar volume, how much volume is in 1 mole. So it's simply rearranging the ideal gas formula by rearranging to have volume over moles. That's molar volume. And of course, when you do that, you get molar volume equals RT over P. And when we plug in the conditions we have at STP, this is just R right here. And this is temperature in Kelvin, on standard conditions, 273. And then divided by standard pressure, which is 1 atmosphere. Guess what, guys? When you plug that in to your calculator, you know what you get? 0.0821 times 273. You get 22.4 liters per mole. That is the conversion factor, again, that we will use for gases, but only if we're under STP conditions. Density of a gas, we can calculate that, and it does vary from gas to gas. Now, there can be a little confusion because we've talked about Avogadro's law, which says that in a certain volume, so I go back to my balloon, in a certain size balloon, regardless of the identity of the gas, you're going to have a set number of molecules in that volume. And it's going to be the same number of molecules regardless of the gas that's in there. So isn't that density, number of molecules per volume? And you just told us that they're all the same regardless of gas. It's close, but not quite. Density is mass per volume, okay, not number of particles. So while the number of particles per volume for a gas is the same, regardless of the gas, the density is not, because the mass of each type of gas for one particle is different for each gas, right? And so as a result of that, even though the number of particles per unit space is the same, the mass per unit space is not. So the density of various gases does vary. The units for density for gases is typically grams per liter. So that's grams of mass particles per liter of volume. One way to get density is to take the molar mass of the gas and divide it by its molar volume. Now, molar volume under STP conditions, remember, is 22.4. That's only under STP conditions. And molar mass, we know how to calculate molar mass, right? So why does molar mass divided by molar volume give you density? As always, we can look at the units. Units will tell us anything and everything. What are the units for molar mass? It's grams per mole, right? What are the units for molar volume? That's what we just did in the previous slide. That's liters per mole. When you put the units for these equations, you can see that moles cancels out, and you're left with units of grams per liter, which is, in fact, the unit that we use for density of gases. So let's calculate the density of a couple gases. Take helium and nitrogen gas, which, of course, is a diatomic. So be careful if you have a diatomic that you account for that in the molar mass. That's the mass of 2 nitrogen atoms divided by, we're doing STP conditions here. It will always specify if it expects you to do STP. And helium has a mass of 4. So which has the higher density? Okay, hydrogen does, or nitrogen does, I'm sorry. Why does nitrogen have a higher density? Because its mass is higher, okay? So the bottom line is, since the molar volume for all gases under STP is going to be the same, 22.4, the density differential between gases depends exclusively on the relative molar masses. So what you can say for certain is the higher the molar mass of a gas, higher the molar mass, the more dense, the higher the density, always. All right, so that's good to know. There is another somewhat more complicated way to calculate the density of a gas, but this formula is important because it also allows us to calculate the molar mass of a gas. So it's very useful. And I don't know how the chem labs have changed with COVID, but there used to be a lab that we would do with gases where you actually are going to use this formula that we're going to derive from molar mass. Now, I'm not going to expect you to go through the steps here and actually derive the formula by rearranging the ideal gas law. I just want you to know briefly where it came from. If you're like me, you're like, hey, where'd you get that from? So we've rearranged the ideal gas before when we were calculating molar volume, or when I was proving where 22.4 liters per mole came from. So we got that far. So now looking at this rearranged form of the ideal gas, can we substitute, what exactly is moles? How do we typically calculate moles? Well, we take the mass of something and divide it by the molar mass, right? So if you have 10 grams of hydrogen gas, for example, and you want to know how many moles, you take that mass and you divide it by the molar mass of hydrogen gas, which is 2.02 grams per mole, right? So that's how we get moles. So I'm going to take this equation and I'm going to do that. Instead of N, I'm going to take N out and substitute in for it mass divided by molar mass. Okay, so I just substituted for N. Now we have molar mass incorporated in the formula for the ideal gas law, so we can actually figure out the molar mass of a gas if we have all the other variables. So let's rearrange first. Let's rearrange this equation first to solve for density. So that's mass over volume, so it'd be grams over liters. which are the units the other way we did density, just with the molar mass. And so that would give us density. Or if we could rearrange this to solve for molar mass, let's see, we would get molar mass equals m times RT, multiply both sides through by RT, and then divide both sides by P. And here it is. So I am going to share with you how I remembered this formula when I learned it. Because I would always find myself getting mixed up. I don't have a good memory for trivia or anything. I'm horrible at trivia. So this is how I remembered it, in case it's useful to anybody. I said mangy mutts. Okay, that's the mangy mutts, put dirt, that's this, dirt over their pee. Mangy mutts put dirt over their pee. So anyway, in case that's useful to anybody. Here's a sample problem to find the molar mass. So let's write our formula first. Mangy mutts put dirt over their pee. Okay, and then let's plug in what we know. We know the density. So plug in that. I'm going to put in all my units to make sure there's not a trick in the units that not canceling or matching. Okay, so R, I'm going to go ahead and assume I can use a 0.08206, but I'm going to put those units in to make sure. Liters, atmosphere, mole, Kelvin. And then I should have written smaller. Then temperature goes on top too. So it's 15 degrees Celsius. I know that has to be in Kelvin. So that is 288 Kelvin for temperature up here. And then all of that needs to be divided by pressure, and I need atmospheres based on the R value I'm using. So here we go. They were nice and gave it to us in atmosphere. So 0.892 atmosphere. All right, so when we plug all that into our calculator, the molar mass we get is 32.3 grams per mole. And right away, you know what, we're not positive what it is because I'm sure there are more than one gas. There is more than one gas with close to that molar mass. But I immediately think about molecular oxygen, which has a molar mass of 32. And that is it for the ideal gas law and all of its manipulations. There are still a couple more gas laws, but I'd say we're more than halfway.